Now there's another reaction that will give us the same product as we got before for the case of reduction of this carbonyl compound into toluene or any other carbonyl compound in general, removing this oxygen and adding 2 hydrogen. And that is done by, if we take amalgamated zinc into mercury, and if we take dilute HCl, if we take this, then we get the same product as before. Mechanism of course will be different, the pathway will be different, but starting and ending material would be same. If you take zinc is the thing that will start the reaction, because mercury is stable. Mercury is not going to do anything. Mercury we just take to dissolve that zinc chip into it. That's the purpose of mercury. Otherwise the reaction will be started by zinc. Zinc is going to lose electron, form a divalent ion, and these 2 electrons have to go somewhere. Now we have studied this kind of thing when we studied pinnacle formation. There we used to take magnesium, and that magnesium used to go and lose some electron, and that electron lost by magnesium used to go into the antibonding of the carbon. So in this case as well, this electron will go into the antibonding of the carbon of this carbonyl group, because that's the carbon which cries for electron, because that's the carbon which is electron deficient. So these 2 electrons are going to go into the this is what we are going to get. We have taken HCl, so that HCl is in dilute form, and there are some amount of H plus roaming around in the system. So that H plus will come. When that H plus comes, it protonates this C minus, it protonates this OH. So we are going to get an alcohol. This aldehyde has been reduced to alcohol. Now H plus, there are more H plus in the system, and those H plus are going to come again and form a bond with oxygen. So now we are going to have a OH2 plus, and this situation we have seen many times before. This water comes out taking away the electron. When it takes away the electron, then the plus charge is developed on this carbon. And there are electrons, there are more zinc atom and more electrons are there in the system. Those electrons will again come into the orbital of the carbon. So this carbon is going to again develop some negative charge. Right? So then there are more H plus in the system as well, released by dilute HCl. And that H plus is going to come again to the C minus. So this is going to become TCH3. So effectively what happened, this oxygen went and 2 hydrogen came in. That's what happened in Wolff-Kishner reduction, and this is what happening in this kind of reduction, which is called as Clemmenschen reduction. Fine. This is called as Clemmenschen reduction, and the final product is same as you had in case of Wolff-Kishner reduction. And in the mechanism, you don't have anything new. All of it, each step, we have seen in some reactions or the other previously. So it won't be difficult for you to grasp this. But make sure that you do the mechanism once in your life, at least once, on your own, on a paper, using a pen, and get to the final product of this toluene starting with benzaldehyde or any other carbonyl compound. Get to the final product such that the C double bond O is reduced, that carbonyl compound is reduced to alkane. Do it on your own, even though it's trivial, but do it on your own. Otherwise, this won't be trivial to you unless you practice it. So the two quick points. The first thing is, I was stressing on dilute HCl all the way along we were learning the mechanism. The reason behind is, you can think of, or it might have occurred in your mind, that when this zinc is losing electron, the electron is going into the antibonding of this carbon. It could have went to H plus instead, because you have H plus in the system, right? This electron can go to H plus, and this H plus can become H dot, and then 2 H dot combine to give H2 gas. This reaction is also a possibility because there are electron in the system and H plus as well. But the reason is, when you take dilute HCl, then the number of HCl in the system is very less. So the number which is this aldehyde is more in number. So when an electron is being released, it will find more aldehyde in its surrounding than H plus. So the probability of this electron reacting with aldehyde is much more than that of reaction with H plus. That's why you take dilute HCl. When you start to increase the concentration, then the reaction with H plus will increase, and this benzaldehyde will show no reaction. So you have to be careful that this HCl is a dilute HCl. Another point is, now there will be different situation in which sometime you use Clemmenschen reduction, sometime you use Wolff-Kishner reduction. For instance, suppose I have this carbonyl group and I have to reach to cyclohexene. Now you have been asked to choose a reagent, suitable reagent to carry out this conversion. Now if you go with Clemmenschen reduction, if you add amalgated zinc along with dilute HCl, then you will do a blunder, because we have learned that this reagent reduces carbonyl group into a alkane, and that's true. This step will occur, no doubt in it, but you have to be keen and look at the reagent, and something else can happen as well, because you have taken a HCl and that HCl can be added to a alkene very well. So actually you will not have this as a final product. Addition will occur, and finally you'll have chlorocyclohexane. Fine, because HCl is there could be addition. So you will not get this as the final product. So to take amalgated zinc along with dilute HCl or to carry out Clemmenschen reduction is not a good idea. In this case, what you have to do is, you should go with Wolff-Kishner reduction, because here the system is basic and this is electron rich. Now base is not going to approach this electron rich thing, because base itself is electron rich. There will be repulsion between them. So once Wolff-Kishner reduction has carried out the reduction of carbonyl group and you have cyclohexene, then there will be no further reaction, because this hydrazine is electron rich, this base is electron rich. There will be no reaction with this high cyclohexene and the reagent that you have taken. So in this case, you have to go with Wolff-Kishner reduction. Fine. So that's the difference. I mean, both are giving the same final product, but you have to choose one of them depending upon the situation. Similarly, suppose if I have this kind of substrate and I want to get this. So I want this bromine to be intact. So if you are going to carry out this conversion using Wolff-Kishner reduction, that means if you're going to take hydrazine and base, then this is not what you are going to get. If this, after the reduction of this carbonyl group, this base is not going to spare this bromine in the ring. This base will carry out substitution. So this Br minus is going to be thrown out by this base, and what you are going to get is cyclohexanol and not cyclobromine. So bromocyclohexane. So that this bromocyclohexane will undergo further reaction to give us cyclohexanol. Fine. So in this case, if you use Clemmenschen reduction, if you take amalgated zinc along with HCl, then because HCl is basic. Because HCl is basic, acidic, so this bromine group will not be affected by the acidic medium. So you are going to end up with this as a final product. So Clemenson reduction will be more suitable than this Wolff-Kishner reduction in this case. Alright, in this case, Wolff-Kishner reduction will be more suitable than Clemenson reduction. So if your substrate is sensible to basic medium, then don't use Wolff-Kishner reduction. If your substrate is sensible to acidic medium, then you don't use Clemenson reduction. So this is the decision that you have to take depending upon the substrate. Alright. So this class of reduction where you are reducing carbonyl group into alkane, carbonyl compound into alkane is done. There are two reactions concerning this class of reduction, Wolff-Kishner reduction and Clemenson reduction that we have seen. So this is done. So let's quickly solve a conversion problem that will also involve these two reactions and the reactions that we have studied recently.